F1 performance are incredible, but I'm so confused by looking at this F1 street tires. They are completely smooth and bold. If I drive my roller car on the highway with bald tires, it's illegal because it's a massive hazard. Why do F1 doesn't have the same tire as the others?
Oh, it's all about the contact patch. For normal car roads, we need those straight grooves to channel away water when it rains, so we don't hydroplane. But on racetrack, F1 cars want the maximum contact with the ground, so a completely smooth tire maximizes the actual surface area that matching the edge.
So more surface area means they get higher friction.
Yeah, exactly. When the car drives at extreme speeds, the friction generates immense heat that usually in between 90 to 110 degrees Celsius. So, this specific soft rubber compound literally undergoes molecular adhesion, means it is chemically softened and glues itself to the track. So, it will maximize the actual surface area and help the car to grip more the road. And for more information, let's shift over this video to see the actual math behind on this concept.
We are analyzing an 1800 kg F1 car going through a 50-degree banked curve. From the telemetry, the car is experiencing an aerodynamic downforce, which also known in fluid dynamics as negative lift of 12,000 Newton. The coefficient of static friction, mu, between the street tire and the asphalt is 1.5. To solve this, we must apply Newton's second law, F equals to ma. Since the car is lifting off the track or sinking into it, the net force perpendicular to the track surface is exactly 0. F equals to 0. So, looking at the perpendicular axis, we have the normal force R pushing through upward, acting against the downward force. The perpendicular component of the car weight, mg cos, and the massive negative lift, Fd, pushing it down. When we rearrange the formula, we get R equals to mg cos theta plus Fd. Substituting our value at 100 kg times gravity multiplied by cos 50 degree plus 12,000 Newton, this will give us a massive normal force of 19,580.4 Newton. And because the maximum available friction is directly proportional to the normal force, Fmax equal to mu R, we multiply that new result by our friction coefficient of 1.5. That gives the car 39,370.6 Newton of pure gripping force. This huge friction force is exactly what Newton's law predicted is needed to provide the centripetal acceleration, so the car can take the corner at blistering speed without slipping.
Wow, so what about when the car straightens up out of the corner and go down to the long straightaway?
Since the air resistance increases non-linearly with velocity, the net driving force drops, which means acceleration is a function of velocity, which is A equal to Fv. And since A is not a constant, we cannot use a standard linear motion equation, so we have to use the calculation to find out this.
Now, what happens when the car gets out of the corner and flies down the straightaway? This brings us to the Chapter 6, Calculus and Variable Acceleration. In the real world, an F1 car doesn't accelerate constantly because resistance changes with speed. Our live telemetry models the acceleration as A equals to 5 minus 0.1 v. Since the acceleration is the rate of change of velocity, we rewrite it as differential equation dv over dt equals to 5 minus 0.1 v. To find the velocity function, we use the separation of variable technique. We bring all the velocity terms to the left and time to the right, which give us 1 over 5 minus 0.1 v dv equals to 1 dt. Next, we integrate both sides. Integrating the left side using the linear fraction rules give us ln 5 minus 0.1 v over negative 0.1, and the right side become t plus c. After multiplying the whole equation by negative 0.1 and combining our constant, we get ln 5 minus 0.1 v equals to negative 0.1 t plus c. To find the value of c, we look at our initial boundary condition. The telemetry shows that t equals to 0 seconds. The car was already moving out of the corner at an initial value of 12 meter per second. Plugging those in, ln 5 minus 0.1 multiplied by 20 equals to c, which simplifies to c equals to ln 3. Now, we just substitute c back and take the optional e of both sides to clear the natural log, and use in that law to simplify the equation 5 minus 0.1 v equals to 3e power of negative 0.1 t. Finally, extraction v gives us our perfect velocity model over time. Vt equals to 50 minus 30 e power of negative 0.1 t. To see how fast the car is going after 10 seconds of acceleration down the straight, we substitute t equals to 10 into the equation. The equation gives us 50 minus 30 e power of negative 1, which calculate to 38.96 meter per second. That is roughly around 140.3 km per hour. This calculus model allows race engineer to map out exactly acceleration profile for track strategy.
Wow, that's awesome. Now I understand. Thank you, Putri.
To wrap things up, it is clear that tires are the most critical performance factors in a Formula 1 race. And through all this study, we had confirmed that after doing Chapter 4 Newton's law, we showed how combining track banking and aerodynamic downforce multiplies the normal force, which providing the massive frictional force needed to sustain high-speed cornering acceleration. And after we undergo the Chapter 6 calculus, we showed that real-world acceleration is variable due to wind resistance. All in all, this provides that mechanics isn't just formula in a classroom, but it is the exact science used to win world championship. Thank you very much.